Imagine I give 10 different people this graph, and I ask them a simple question. Draw the best straight line. You'll probably get 10 different answers. Some too steep, too flat, some that just feel wrong. And yet in machine learning, we somehow expect the computer to choose. Not randomly, not by guessing, but mathematically. So this raises a surprisingly deep question. When we say the best line, what do we actually mean? Because once we answer that question, we've secretly understood the foundation of linear regression. So suppose we settle on a line, not perfect, but reasonable. Now we need a way of measuring something important. How wrong is this line? Because the line makes a prediction. For every point on this graph, it secretly says, if X is here, then I think Y should be here. But reality doesn't always agree. Sometimes the actual point sits above the line, sometimes below, and this tiny vertical distance is what we call a residual. You can think of it as the error, the disagreement, the distance between what actually happened and what the line predicted. Mathematically, we write it as actual minus predicted. If a point sits above the line, the residual is positive. If it sits below, negative. And intuitively, that feels useful, right? A tiny residual means good prediction. A huge residual means, okay, something went wrong. So maybe, just maybe, we found our answer. Maybe the best line is simply the one with the smallest total error. But there's a problem, a surprisingly sneaky one. So our first instinct seems reasonable. Take all the errors, add them together, and choose the line with the smallest total. Simple, elegant, done. Except watch what happens. Some points sit above the line, positive residual. Some sit below the line, negative residual. And at first, that doesn't seem like a big deal until we start adding positive, negative. Something strange happens. They begin to cancel. And suddenly, a terrible line, one that is obviously missing the pattern, can still claim the total error is still equal to 0. That feels wrong. Because look at this line, it's clearly bad. The pattern of the data almost screams, tilt me downwards. And yet, mathematically, we somehow ended up saying, yeah, 0 error. The problem is subtle. We need a way to punish mistakes without letting them cancel. Something where big errors stay big, small errors stay small, and everything becomes positive. So here's a question. What if, instead of measuring distance, we measure area? So adding the errors doesn't work. Positive mistakes cancel negative mistakes, and somehow a terrible line can pretend to be good. But what if, instead of looking at the raw error, we transformed it? Take a residual and imagine building a square from it. Not a metaphor, but an actual square. A tiny error creates a tiny square. A bigger error creates a much bigger one. And suddenly, everything beautiful happens. Every contribution becomes positive. No cancellation, no hiding, no sneaky tricks, because areas can't cancel. A square of area 4 doesn't magically disappear because another area showed up on the other side. And something even more interesting happens. Big mistakes become dramatically more expensive. Double the residual, and the square doesn't just double, it explodes. Small mistakes, barely punished. Huge mistakes, impossible to ignore. And intuitively, that feels right. Because if a line makes one prediction wildly wrong, we want to care about it a lot. So instead of minimizing the raw error, we ask a new question. Can we find a line that makes the total area of all these squares as small as possible? And just like that, we arrive at the idea hiding underneath linear regression, least squares. So now we have the idea. The best line is the line that makes the total square error as small as possible. But if we want a computer to find that line, we need to turn this idea into an equation. A straight line can be written as predicted y is equal to mx plus b. Here, m controls the slope and b controls where the line crosses the x-axis. So for one data point, the line predicts m of xi plus b, but the actual value is yi. So the error for that point is actual minus predicted, yi minus mxi plus b. And because raw errors can cancel, we square it. Now each point contributes yi minus m of xi minus b all squared. That is the square from earlier, but written algebraically. And because we don't have just one point, we add this over every point in the dataset. That gives us the cost function. The j of theta of m and b equals the sum of all those squares errors. And this little function is now the entire game. Give it a slope and an intercept, and it gives back a score. A bad line gets a big score, a better line gets a smaller score. So finding the best line means finding the values of m and b that makes the score as small as possible. Now the question becomes, how do we actually find them? So we now have a score, a way to measure how good a line is. Give me a slope, give me an intercept, and the cost function gives back a number. Small means good, large means bad. But something interesting happens when we zoom out. Instead of trying one at a time, imagine trying every possible line, every possible value of m, every possible value of b. And for each pair, we calculate the total squared error. Suddenly, what looked like an equation becomes a landscape. High up here, the error is huge. These are terrible lines, too steep, too flat, clearly missing the pattern. But as we move downwards, the score gets smaller, the line gets better. Until eventually we arrive here, the bottom of the bowl, the lowest possible error, the line that minimizes all those squares from earlier, the line we've been secretly searching for this entire time. And geometrically, this is beautiful. Finding the best line has quietly become find the lowest point in a landscape. So naturally, the next question becomes, how do we actually get there? How do we mathematically find the bottom of the bowl? And for that, we need calculus. All right, so we found the landscape, the giant bowl of error you can think of. And somewhere at the bottom is the best possible line. So now the question becomes, how do we mathematically find the lowest point? Well, in calculus, there's a clue. At the top of the hill, the slope changes. At the bottom of the valley, something special happens. For just a tiny moment, the surface becomes flat. The slope becomes zero. And that means if we want the bottom of this bowl, we need to find where the slope disappears. But wait, there's a complication. Our cost function depends on two things right now, the slope m and the intercept b. So let's simplify this problem. For now, pretend we only change b. Imagine sliding down the line up and down, keeping the slope fixed. How does the cost function change? That answer is answered by a partial derivative. We take the derivative of the cost function with respect to b. At first, this looks intimidating, but essentially it's just calculus. We differentiate each term, apply the chain rule, and something surprisingly clean happens. The derivative becomes minus 2 times the sum of yi minus m of xi minus b. And now comes the key idea. At the minimum, the bowl becomes flat. So we set the derivative equal to 0. Suddenly, this giant optimization becomes an equation, an equation our best line must satisfy. But we're only halfway there, because the slope m still hasn't had its say yet. But the line still has another freedom, the slope m. Because even if the line sits at the right height, it can still lean the wrong way. Too steep, too flat, or somewhere in between. So now we ask the second question. What happens to the cost when we change m? This time, we take the partial derivative with respect to m. And just like before, it looks intimidating at first, but underneath is the same idea of calculus. we just carefully differentiate it term by term. The square stays, the chain rule appears again, except now there's something extra because m multiplies x, and after simplifying, something elegant appears. The derivative becomes minus 2 times the sum of xi multiplied by yi minus m of xi minus b. And once again, we return to the same geometric idea. At the bottom of the bowl, the surface becomes flat, so once again, we set the derivative equal to 0. Now we have something beautiful. Not one equation, but two. One coming from B and one coming from M. Two constraints, two unknowns, and hidden inside these equations is the best line. All right, we've done the hard part. Two derivatives, two equations, and hidden inside them, the best possible line. So now it becomes a familiar problem, just algebra, simultaneous equations. We take these two equations and solve the system. At first, it looks messy, summations, m's, b's, terms everywhere. But notice something important. These equations aren't random. They're structured. Every symbol means something. Every term came from the geometry of the problem. So let's isolate one variable, maybe let's just solve for b, and substitute it into the other equation, slowly, carefully, no magic. And after a bit of algebra, something remarkable starts to happen. The mess begins to collapse. Terms cancel, expressions simplify, patterns emerge, until eventually out comes a formula for the slope. And there it is, the value of m, the slope of the best fit line. Not guessed, not eyeballed, derived. And once we know m, finding b becomes straightforward. We plug it back in, simplify, and recover the intercept. And just like that, after all the geometry, all the derivatives, and all the algebra, we finally have the line. The best line chosen mathematically, the one that minimizes all those squares. But if you're feeling slightly exhausted, you're not alone. Because there's a problem, a really serious one. What happens when we don't have one feature, but 10, 100, 1000? So we found the line, we built squares, constructed a cost function, took derivatives, solved a system of equations, and finally arrived at the best answer for one feature. One. But real machine learning problems rarely look like this. Instead of predicting from height alone, we also include age, sleep, income, temperature, blood pressure, exam scores. Now, suddenly, the line becomes something bigger, not y is equal to mx plus b, but y is equal to theta 0 plus theta 1, x1, plus theta 2, x2, plus theta 3, x3, and so on and so forth. And here's the problem. Our beautiful derivation starts to become a nightmare. Now we're taking derivatives with respect to theta 1, theta 2, theta 3, theta 4, theta 5. Every new feature means another derivative, another equation, another unknown, more algebra, and more bookkeeping. And eventually, this little derivation we've just done, me and you, tends to become completely impractical. Not impossible, just painful. Because imagine doing this for 10 features, 50, 100. There has to be a smarter way, a language designed for handling lots of variables at once. And this is where linear algebra quietly enters the story. Because instead of solving for one messy equation at a time, what if we could write this problem all at once? All right, let's stop suffering for a second. Because all of this, the derivatives, the substitutions, the endless bookkeeping, it came from one problem. We were trying to juggle too many variables one at a time. So instead, let's zoom out and rewrite the entire problem in a smarter language. Suppose every row in this matrix represents one observation, one person, one house, one patient, one data point, whatever this may be. And every column represents a feature, height, age, income, blood pressure, whatever information we think might matter. But notice something strange. Why is there a column of ones? Why are we wasting space? Remember the intercept, the little constant term, the thing we used to call b. If we multiply anything by 1, it stays unchanged. So the first column quietly handles the intercept for us. No special treatment, no separate equation, just mathematics doing bookkeeping. And now instead of writing theta 0 plus theta 1, x1 plus theta 2, x2 plus theta 3, x3 over and over and over again, we compress everything into one vector. These are the parameters, the numbers the model is trying to learn, the weights, the knobs we adjust. And here comes the beautiful part. When we multiply the feature matrix by the parameter vector, something familiar quietly appears. Prediction after prediction, row by row, observation by observation. What looked terrifying at first turns to be astonishingly simple. We basically said, bro, let's stop repeating ourselves and let's just put it all into one neat system, one clean expression. Y hat equals x theta. That entire mess, all those giant equations compressed into 3 symbols. And suddenly the problem feels manageable again. But what if we can rewrite predictions this way? Can we rewrite the errors too? Land. So instead of one residual, we get a whole vector of them. Take the actual outputs, subtract the predictions, and suddenly we have every error all at once. The residual becomes y minus x theta. And if you remember, our original goal wasn't to look at errors. We squared them, added them up, and tried to make that total as small as possible. Now, something elegant appears. When we multiply a vector by its transpose, we're secretly doing the same thing. Square, add, again and again and again. If you don't understand linear algebra at this point, it doesn't matter. As long as you understand the matrix multiplication, which is just squaring the errors together, that's more than enough at this point. So our entire least squares objective can now be written as j of theta equals y minus x theta transpose multiplied by y minus x theta. And look at what just happened. The giant summation, the endless notation, all that clutter collapsed into one clean expression. Same idea, same geometry, same least squares intuition, just in a language that scales. And I think we should stop and appreciate linear algebra for a second. It's literally just a language that helps us compress data such that we can only write it once and not just repeat ourselves. Because once we have the cost function, we can finally do what calculus does best, differentiate it, and find the bottom of the bowl. All right, we've rewritten the problem, the predictions, the residuals, even the cost function, everything compressed into one elegant expression. But underneath all the matrix notation, nothing fundamental has changed. Our goal is still exactly the same. Find the bottom of the bowl, the smallest possible error. And calculus gives us the same strategy. At the minimum, the surface becomes flat, the slope disappears. So once again, we differentiate, but this time with respect to m and b separately. We differentiate with respect to the entire parameter vector, theta. One derivative for every parameter all at once. Now, I'll spare you the matrix calculus details, but underneath all this notation, the same story is happening. Expand, differentiate, simplify. And something beautiful appears. The gradient becomes x transpose times x theta minus y. And just like before, we go back to the geometric idea. At the bottom of the bowl, the slope becomes 0. So we set the derivative equal to 0. Suddenly, our optimization problem becomes x transpose x theta minus y equals 0. And then we can move things around, cancel the terms, and after simplifying, we arrive at something extremely remarkable. X transpose X theta equals X transpose Y. This equation has a name, the normal equation. And hidden inside it is the best fit solution, the exact parameters that minimize the total squared error. But we're still one final step away because theta is still trapped inside the equation. So the question becomes, how do we actually solve for it? So after all of that, we finally arrive here. X transpose X theta equals X transpose Y. At first glance, this might look intimidating, like we've somehow made things more complicated, but something important has happened. Look closely. This one equation contains everything, every feature, every observation, every parameter, all compressed into one clean mathematical object. And remember our goal. We're not trying to admire the equation. We're trying to solve it. Because hidden inside is theta, the parameters, the weights, the numbers defining our best fit model. So how do we isolate them? Well, the same way we solve ordinary equations, carefully, step by step. If we want to get rid of x transpose x, we multiply both sides by its inverse. And something beautiful happens. On the left, x transpose x cancels itself out, just like multiplying a number by its reciprocal, leaving behind only theta. And suddenly, after all the all right, before we move on, there's something deeply satisfying hiding here. Because earlier we suffered. We built squares, took derivatives by hand, solved equations by hand, carefully worked through all the algebra just to find two numbers, m and b. And now we've written everything using matrices. Linear algebra, vectors, transpose symbols, inverses, enough to make notation feel like an entirely different problem. But here's the strange part. It's not different. Suppose we go back to our simple case, just one feature, one straight line. If we build this entire feature matrix exactly the way we described earlier and let theta contain m and b, then something remarkable happens. When we expand the normal equation, the giant matrix expression begins to collapse into something very familiar. These equations, we've seen them before, exactly before. The same equations we got from partial derivatives, the same system we solved by hand. And when we solve them, the same values appear, the same m, the same b, exactly. So this matrix approach didn't replace the old mathematics. It revealed what the mathematics was secretly doing all along. Same geometry, same least squares idea, same answer, just written in a language powerful enough to scale. One feature, 10 features, 100 features, the framework stays the same. And that is the real magic of linear algebra. Instead of just repeating ourselves over and over and over again, we can just do the exact same process just by putting everything into a matrix and then just taking its inverse and multiplying everything. And I think that's such a beautiful thing about linear algebra. So it feels like we're done. One elegant formula, one clean answer, just plug in the data and out comes the best model. Except there's a tiny catch. This part, the inverse, because hidden inside our solution, we quietly assume something, that this matrix X transpose X can actually be inverted. And surprisingly, that's not always true. Imagine we're predicting something about people, and we include two features, height in meters and height in centimeters. At first, that sounds reasonable. More information is good, right? Except, look closely. These two aren't independent features. One is just the other multiplied by 100. Same information, different units. Geometrically, something strange happens. The columns of our matrix begin pointing in the same direction. Not new information, not a new dimension, just repetition. And when this happens, something breaks. The matrix loses something important, its inverse. Suddenly, this step stops existing. No inverse, no unique solution. Now, Before this sounds terrifying, don't worry. In practice, we usually fix problems like this, sometimes by removing redundant features, something sometimes through techniques like regularization. But the important idea is this: the normal equation is elegant, powerful, beautiful even. But like most mathematics, it comes with assumptions, and understanding those assumptions matters. So let's step back for a second. We started with something deceptively simple: a cloud of points, messy, noisy, human, and a question: can we draw a line that somehow captures the pattern hiding underneath? At first, that felt subjective, something you might eyeball, something you might argue about. But slowly the problem sharpened. We needed to measure error. So we introduced residuals, tiny disagreements between what actually happened and what the line predicted. Then came a subtle problem. Positive and negative errors could cancel. A terrible line could somehow pretend to be good. So we squared them, turned distance into area, and suddenly the goal became geometric. Find the line that makes the total square error as small as possible. Least squares. From there, things became mathematical. We built the cost function, took derivatives, solved the equation, and something beautiful happened. We found finding the best line was secretly the same thing as finding the bottom of a landscape. Then, just when the algebra began to feel unbearable, linear algebra quietly stepped in. The matrix collapsed, predictions, residuals, the cost function, all rewritten in one elegant language. Until eventually everything led here. Theta equals x transpose x inverse a times by x transpose y. One compact expression containing geometry, calculus, optimization, and data. That is linear regression. Simple in idea, surprisingly deep in execution, and quietly sitting underneath a huge amount of modern machine learning. But there's one final question. What happens when the thing we're predicting isn't a number? What if the answer is yes or no? Fraud or not fraud? Malign or benign? Because suddenly, a straight line predicting 1.7 cancers feels a little strange. So, next time, we leave regression behind and enter the world of classification. That is episode 1. Thank you.